Hello! Time for a couple applications of the Doppler effect. The Doppler effect describes and characterizes the change in frequency between the light emitted and the light received when emitter and receiver are in relative motion. This can also be thought in terms of wavelengths, as wavelength is the speed of light over the frequency. There are many applications of this effect, but probably it is most relevant in astronomy, where it is used to estimate the speed of distant objects with respect to us. For example, it's used to measure the recession speed of galaxies. We know that the universe is expanding, and the farther away the galaxy is, the fastest its recession speed. This is known as the Hubble law. Observing the redshift due to Doppler effect, we can estimate this speed. Astronomers also use it to detect exoplanets, planets revolving distant stars. Because of gravitational pull of the planet on the star,
gravity is pulling all the stars in the area towards this spot.
The star can be wiggling towards and away from us, giving a blue and a red shift of the light emitted. From Doppler effect, we can calculate the speed of this wiggling motion and from there estimate the characteristics of the planet, making the star wiggle. Doppler effect can be written in terms of the frequency or the wavelength. If we square this equation, we multiply this by 1 plus beta, we factor out beta, and we solve for the beta speed. We get this ratio that gives us the speed beta at which the star is wiggling about a common center of gravity between the star and the planet. From Kepler's third law, we can find a relationship between the radius of the orbit of the planet and the mass of the star. The centripetal force experienced by the planet is mv squared over r. The gravitational force is gm prime over r squared. Using the fact that the speed is 2 pi r over t, being t the period of the orbital motion of the planet around the star, solving for the radius of the orbit r, because the center of mass is at rest and because of conservation of linear momentum, we have that m of the planet times v of the planet is equal to m of the star times v of the star. The speed of the planet is 2 pi r over t, so we have that the mass of the planet can be estimated if we know the speed of the star, the mass of the star, the radius of the orbit, and the period of the motion. If we substitute our previous result for the radius of the orbit, so we can estimate the radius of the orbit and the mass of the planet if we know the period, the speed of the star, and its mass. We can measure by observing the period of the blue and red shift of the light emitted by the star. We can measure the speed of the star using the Doppler effect, and we can estimate the mass of the star by other astrophysics calculations. Another application of the Doppler effect, as I mentioned in the previous video, is the traffic radars. In those cases, there is a signal sent to your car, the signal is reflected off of the car and is detected back. Here we have to apply the Doppler effect twice. If your car is going away from the detector, the radar box sends a radio wave of frequency nu. Your car detects a redshifted frequency nu prime and remits that frequency nu prime. The detector receives a redshifted signal nu 2 prime. Because the process is so quick, even though you could be accelerating, we can assume that the speed of the car is constant throughout the process. If you are driving at 140 kilometers per hour, 88 miles per hour! The frequency used are between 10 and 10.5 gigahertz. Using a frequency of 10 gigahertz gives a relative difference of about 2.6 times 10 to the negative 7. May the science be with you.